We are going to discuss about the energies of orbitals or energy level diagrams. Energy level diagrams. What do you mean by energy level diagrams? A diagram representing the relative energies of various orbitals in an atom is called energy level diagram. First, let us draw the energy level diagram of hydrogen atom. Hydrogen atom. Now, hydrogen atom, we have here the lowest energy as n is equal to 1, and energy is increasing in this order, in this way. So here we have n is equal to 1, then n equal to 2, next level is n is equal to 3, n is equal to 4, etc. Now, n is equal to 1, we have our 1s orbital. Because n is equal to 1, we have only 1s orbital. N is equal to 2, we have 2s and 2p orbitals. N is equal to 3, we have 3s, 3p, 3d orbitals. Now, in n is equal to 4, we have 4s, 4p, 4d and 4f orbital. Now, we know that in hydrogen we have only one electron. The atomic number of hydrogen is 1, and that one electron will be present in the lowest energy state, that is n is equal to 1, and one electron in hydrogen is present in 1s orbital. Okay, and we call this low energy state of an atom as the ground state. And we know this electron in 1s orbital can get excited, or it can go to higher energy levels, that is 2s, 3s, 4s, like that. Okay, so in the energy level diagram of hydrogen, I can write the increasing order of energies of various orbitals as 1s less than 2s is equal to 2p. You know, 2s and 2p are in the same level. Less than 3s is equal to 3p is equal to 3d. Less than 4s equal to 4p equal to 4d equal to 4f. So this is the order of energies of various orbital in case of hydrogen atom. Okay, increasing order. Now, you can see in hydrogen atom, all the orbitals with same n value will have same energy. That is, S and P with n is equal to 2 has same energy. SPD with n equal to 3 has same energy. Now, and we already discussed the term degenerate orbitals, 2s and 2p here. They have same energy, so we can call them degenerate orbitals. 3s, 3p, 3d, they have same energy in case of hydrogen atom. So we can call 3s, 3p, 3d here as degenerate orbitals. Now let us see the energy level diagram for a multi-electron atom. Hydrogen had only one electron. Now suppose there are two or more than 2 electrons, then the energy level diagram is different from hydrogen atom. So next we are going to draw the energy level diagram for multi-electron atom. Now, the diagram is, again, we have here n is equal to 1. Here we have energy increasing in this order. Now, in multi-electron atom, here this is our 1s orbital. Now, after 1s we have 2s with higher energy. Then we have 2p, and 2p we have 3 2p orbitals. Then we have after 2p 3s, then after 3s we have 3p orbitals, and there are 3p orbitals, px, py, pz. I drew 3 dotted lines. After 3p, it's not 3d, I have 4s orbital. After 4s, I have 3d orbitals. Because there are 5d orbitals, I drew 5 dotted lines. Now look at the order of energies of orbitals in multi-electron atom. If you are to write in increasing order, you can write the order as 1s, less than 2s, less than 2p, less than 3s, less than 3p, less than 4s, less than 3d. So this is the order of orbitals in multi-electron atom. Increasing order of orbitals, increasing order of energies of orbitals in multi-electron atom. And the order is 1s, less than 2s, less than 2p, less than 3s, less than 3p, less than 4s, less than 3d. Now, why is there a difference in the order of energy level of hydrogen and this multi-electron atom that we will discuss? Before we discuss that difference, let's see some observations from the energy level diagram of multi-electron atom. And we know most of the atoms in chemistry or elements, they are multi-electrons are present. So let's see the observations made from this. The first observation is the subshell of a particular shell do not have same energy here. That is, you can see 2s and 2p. In case of hydrogen, the 2s and 2p was of same energy, but here the 2s and 2p are of different energy, and 2s has lower energy than 2p. Okay. Now the second one is, in a particular shell, subshell with lower value of L has lower energy. That is, 2s and 2p. The N value is the same, that is 2. But L value is different. L value for S is 0 and L value for P is 1. So, for a particular shell, the subshell with lowest L value has the lowest energy. So, when you compare the energies of 2s and 2p, 2s with L value 0 has the lowest energy compared with 2p. Now, again you can see when you compare 3s, 3p and 3d, 3s has lower energy than 3p than 3d. Now, the order of energies of various orbitals in or various subshells can be predicted with the help of N plus L rule. Suppose you are given two orbitals and you are asked to find out which orbital has higher and which has lower energy. We can use this N plus L rule. Now, the rule is this: the lower the value of N plus L for an orbital, the lower is its energy. Okay, lower the value of N plus L for an orbital, lower is its energy. I'll give an example. Now, you are asked to find out whether 4s or 3d, which has higher and lower energy. So, let's apply N plus L rule. For 4s orbital, we have N is equal to 4 and L is equal to 0, because for S subshell L value is equal to 0, we get it as 4. Now for 3D orbital we have 3 plus L is equal to SPD 0, 1, 2. So 3 plus 2 is equal to 5. Now you can see that 4S has 4 and 3D has 5, N plus L. So the rule is the one with lower N plus L value will have lower energy. So we can say 4S has lower energy than 3D. So you can see this order we have written here, 4S has lower energy than 3D. So it can be proved with N plus L rule. Now suppose the two orbitals have same N plus L value. In that case, the orbital with lower value of lower value of N will have lower energy. Okay, so if two orbitals have same n plus L value, then the orbital with lower value of n will have lower energy. Example, 4s and 3p. Let's apply n plus L to this. 4s will be 4 plus 0 is equal to 4, and 3p will be equal to 3 plus 1 equal to 4. Now you can see this 4s and 3p has same n plus L value, which is equal to 4. So again, what is the rule? The one with lower n value, which is the one with lower n value, 3p has lower n value because n is equal to 3. So 3p has lower energy than 4s. So we can say the energy of 3p is less than 4s. Okay. Now next observation is similar orbitals of different atoms do not have same energy. That is, if you look at the atom hydrogen, lithium, sodium, potassium, suppose the orbitals are 2s, 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 and you can see that the energy of these orbitals is not the same of hydrogen, lithium, sodium, potassium. They don't have same energy. The energies of orbitals in the same subshell decreases with increase in atomic number. So you can see here the atomic number of potassium is the highest. So the energies of 2s orbital decreases with increase in atomic number, which means energy of 2s orbital of hydrogen is greater than, lithium greater than, sodium greater than potassium. Okay, so these are the different observations that we get from the energy level diagram of a multi-electron atom. And I told you this energy order, increasing order of energies of orbitals, this order you have to learn by heart up to 3D. So the order is 1s less than 2s less than 2p less than 3s less than 3p less than 4s less than 3d. Okay. Now next let's see why is there a difference in the order of energies of hydrogen and multi-electron atom. The reason is this. In hydrogen atom we know the only force of interaction is the force of attraction between the electron and the nucleus, because we have only one electron in hydrogen atom. So the only possible interaction is between the electron and the nucleus. But in case of multi-electron atom, we have two types of interactions. One is the force of attraction between the electron and the nucleus, and second is the force of repulsion between the electrons. And these repulsive forces are mainly between the electrons present in inner and outer orbital. Okay. Now also we know that the force of attraction on electron increases with increase in the positive charge of the nucleus, and we call that positive charge on nucleus as nuclear charge. And also you can see the electron that is close to the nucleus can experience that full or net positive charge on the nucleus. So the net positive charge experienced by an electron from the nucleus is known as effective nuclear charge. Denoted by ZEFF, that is Z effective. So Z effective is the effective nuclear charge or the net positive charge experienced by an electron from the nucleus. And the effective nuclear charge experienced by an electron depends upon the shell and shape of orbital in which the electron is present. Now I told you there is a force of repulsion between the inner and outer electron. So inner electron means the electrons which are close to the nucleus. They can attain that full positive charge on the nucleus. Okay, so what they do is these electrons closer to the nucleus, that is the inner electrons, will not allow the outer electrons from attraction with the nucleus. These outer electrons also want to get attracted to the nucleus, but who will prevent them from this attraction? The inner electrons. And we call this, that is the prevention of inner electrons, or the process by which the inner electrons will shield the outer electrons from attraction with the nucleus. That process is known as shielding effect. Shielding effect, or we can also call it as screening effect. Who will screen whom? The inner electrons will screen the outer electrons from attraction with the nucleus. Okay, so nuclear charge means the positive charge present on the nucleus, that is Ze, is called nuclear charge, and the net positive charge experienced by an electron from the nucleus is called effective nuclear charge, and the inner electrons have more Z effective because they are closer to the nucleus, and the inner electrons will prevent the outer electron from attraction with the nucleus, and we call that as screening effect or shielding effect of shielding of outer electrons from inner electrons from the attraction with the nucleus. Okay, or shielding of outer electrons by inner electrons from attraction with the nucleus. Okay, now you can see that the screening effect or shielding effect, you know that S orbital is closer to the nucleus, then comes P, then D, then F. So we can see that the screening or shielding effect of orbitals is in the order S greater than P, greater than D, greater than F. So this is the order of screening or shielding effect of orbitals. Now again we know that the force, who will experience, the electron present in S orbital will experience more nuclear charge. Because S orbital is closer to the nucleus. So the attractive force experienced by electron in various orbital will also be in the same order. S greater than P greater than D greater than F. But the order of energies of subshells will be in the order S less than, P less than, D less than F. That is, the energy of S orbital is less than P, less than D, less than F. So these are the reasons for the difference in energies of orbitals in hydrogen and in multi-electron atom, because in multi-electron atom we have inner electrons which shield the outer electrons from attraction with the nucleus. Okay, thank you.